All right. Multiple comparisons. Now, here's probably a topic that you didn't cover in an intro stat course. And if you did cover it in an intro stat course, I would say that you probably had a really good intro stat course. All right, power issues. We have an issue here with error inflation for when we do multiple tests. And this is what's sometimes called alpha inflation. There are a couple of different values that we can talk about. We can talk about pairwise alpha. That's the probability of making a type 1 error for any single comparison. So overall, when we do that F test, we have alpha of 0.05. However, since we have multiple groups, we want to also ask questions sometimes about which groups actually differ from each other. We can't just look at the means and say that the groups differ from each other. We have to provide some additional statistical test. Now, the problem is that when we have, say, 3 groups, we end up doing 3 different comparisons, and we want to compare all the group means to each other. What that means is we're doing 3 tests, all of which have alpha of 0.05. That would be called the pairwise alpha. When we do multiple tests, though, we end up with a family of tests, and we also have a family-wise error rate. Then that's going to reflect not the probability that we made a mistake on any individual test, it's the probability that anywhere within those 3 tests, we have made an error. So that's family-wise error rate. Family-wise error rate really drives our decisions around multiple comparisons, and we'll talk about some strategies for dealing with this. The calculation of the family-wise error rate, it's simply 1 minus the pairwise rate to C, the power of C, which is the number of comparisons. And one thing we can see from this little table, the more groups we have, the bigger a chance that we have made a type 1 error somewhere along the line. With 2 groups, it's of course just 0.05 because we're only making 1 comparison. Once we hit 3 groups, we're making 3 comparisons. We have a 14% chance of having made a type 1 error somewhere along the way. Similarly, with 4 groups, you can see that jumps up to 0.46. 5 groups, we're already at 40%. 6 groups, 54%. So we're seeing that it's getting to look really, really likely that we're going to make that a type 1 error. Again, type 1 error, false positive, falsely rejecting a null hypothesis. It's actually true. So one thing that this tells us is that there are some real challenges when we're doing these sorts of comparisons. Now, there are many, many different test options that we're going to see. The first time I taught a course on ANOVA, I used a book by Roger Kirk. It was very, very famous contributor to the field. And in Kirk's book, there is, I think, a 65-page chapter on all the different multiple comparison tests. And you can still see some of the vestiges of that in my handouts with all the different formulas with, I use the psi symbol. I just don't have the heart to take those out of those handouts anymore, but we're not going to calculate them by hand, of course. A couple of distinctions that we'll see here. First, was the test a priori or post hoc? And also, how many comparisons are we making and against what? A priori, that just means that you have specific hypotheses that you laid out before data collection. If you do that, you get to use a more liberal test. And by more liberal, I mean a test that makes it a little easier to reject the null hypothesis. Post hoc test. Basically, the idea here is you don't have any idea whether there'll be differences, but if there are differences, you want to find them. So this is generally a case where you're looking for every difference, any possible difference. Multiple comparison tests, when I think about this is a really good example of how precedent and tradition guides statistical practice. Multiple comparison tests are extremely common in ANOVA. You'd never get away with doing a test without doing one. However, you go over to multiple regression and you could have a model that has 5 predictor variables. That's doing 5 tests, right? All with alpha of 0.05 with no alpha adjustment in sight. So it really does kind of speak to a somewhat arbitrary nature of these decisions, and how we've always done it tends to guide how we do it in the future. All right, some of the tests that we'll talk about. The Bonfironi test, attributed to Carlo Emilio Bonfironi, likely the first of the tests, and it's the simplest of the test. What did Bonfironi do to solve this problem? Well, simply divide your alpha by the number of comparisons. If you have 3 comparisons, take alpha divided by 3, 0.0167. I'm not a mathematical whiz. I've just seen that number many times before there. Alternatively, even easier, you can do these comparisons. You can do these comparisons with a simple t-test, and then take the probability of that test and multiply it by the number of comparisons. Same thing as, same approach, different way. This is likely the first multiple comparison test. It's very simple, and it was primarily used for a priori situations. One of the critiques of the test is it's a little too conservative. We don't cover this test, but it is, but Bonfironi, that's fun to say. I really enjoy talking about Bonfironi. So Bonfironi's always got a place in my class, regardless of whether we use the test or not. All right, Dunnett's test. This is an a priori test for comparing all groups to a single other group. Everything compared against another group. In our example, maybe we wanted to compare everything to group 3. So our comparisons would be group 1 versus 3, group 2 versus 3. We'd never compare 1 and 2 in that situation. This is most commonly used when we have a control group and multiple treatment groups. Fun facts about Dunnett. Dunnett served in World War II, and he was just about to leave for the Pacific when, as he put it, the war suddenly ended because of a couple nuclear bombs. So he decided to go to graduate school because he didn't have anything to do. Interesting start to his statistical career. All right, the Tukey test. Tukey was a mathematician best known for the Tukey honestly significant difference, or HSD test, also box plots. It is a very conservative post hoc test, but it's probably the one that's most widely applied. It compares all pairs of means, and again, like I said, people often even use this for a priori, whereas I would strictly use it for post hoc. Of course, one of these pictures is of John Tukey, the other is of John the Turkey. I'll leave that for you to figure out. Perhaps you'll Google it or something. Here is a chaffey test, Henry chaffey, post hoc test for comparing all pairs and all combinations of pairs. So not only are you comparing the individual pairs, with the Tukey test, you're combining groups and comparing the average of them to other groups. So all those different things. A really fun fact here, if you look at this picture of chaffey, chaffey suffered multiple broken noses resulting from fistfights with other statisticians. That's actually not true, but I always think it must be when I see a picture of him. All right, orthogonal contrasts. These are very liberal. They're basically like t-tests without any alpha adjustment. You would use them exclusively for a priori. There's a limit to the number you can do. Number of groups minus 1 sets the number of comparisons we're allowed. We do this by setting different weights for comparisons. So if you want to look at, and we'll take a look at those weights in a second. None of our comparisons can contain overlapping information. For example, if I can compare group 1 and group 2 to group 3, I can no longer compare group 1 and group 1 or group 2 individually to group 3. That because it's overlapping information. I already know something about that. There are going to be negative and positive weights assigned to variables to make these contrasts. The weights themselves must sum to 0. So you'll have the positive end adding to, and in this case, I have them add to 1. They can add to any number, just stick with 1 while you're learning it though. So the first comparison, I'm comparing group 1 and group 2 averaged. And the way I do that is I simply assign both of them a value of 0.5, and I compare that to group 3. So it's just like saying average of group 1 and 2 minus the average of group 3 and doing a t-test. The next contrast I can do here, the only thing left for me to do is possibly compare group 1 and 2, since I can't compare 1 individually to 3 or 2 individually to 3 because that line was already crossed. So I can't do that, compare any of those comparisons. Only thing that hadn't been compared at this point was 1 versus 2. To give you more practice with this, because I know that this is always a topic that's challenging for students, and certainly it was it's been that way for ages. It was challenging when I was a grad student. We've got an example from a study I did way back in grad school. It's got 6 different research conditions. What the study comprised of is participants came and they in this case they watched a video where somebody described their qualifications and their experiences, and they were ostensibly applying for an HIV director position, and we varied things to give us 6 different versions. In the first version, there was an unqualified gay man. I think he reported his experiences were volunteering to hand out condoms on Valentine's Day or something like that. Unqualified heterosexual man. How do we make that distinction? Well, they mentioned something about their partner and the gender of their partner, and how an ex-partner had they got interested in HIV activism because an ex-partner had told them that they had tested positive. Next, we have the ambiguously qualified conditions. In these conditions, it wasn't clear what the person's experience was. It wasn't clear what exactly they had done at their position. So, kind of left participants to kind of fill in the blanks. And then the highly qualified condition. This is one where basically they had done, they were in an assistant director job where they had done all of the listed job duties. These contrasts will generally match specific research questions. So you can see in the first contrast, I've got 2s on the first 2, and then 1s or negative 1s on the other 4. So one question we can ask here, kind of a manipulation check even, did those participants rate the non-qualified person worse than all of the other conditions? And I say that's kind of a manipulation check because we're checking on that qualification manipulation there. Next, we can distinguish between the high quality and the ambiguous. Was there a difference between those two groups? So we see non-qualified, they get 0s. What that means is they don't even play into this contrast. Here we've got 1s for the AQs and negative 1s for the HQs. Next up, we start to compare the different pairs that we haven't compared. So we compare the gay and the heterosexual not qualified, the ambiguously qualified, and the highly qualified. Those are the remaining comparisons. And just for your interest, I have what turned out in terms of the study the last yes was really the most focal hypothesis within the study. So this is a technique that would need to really fit nicely with specific research hypotheses. And techniques like this, these experimental design techniques, a lot of them come out of Fisher's work.